From recalling what we did on Thursday. So recall. For a subset G in complex numbers, which we always identify with pairs of real numbers, open, we considered a function so also treated as a map from G to R squared. I mean, it's the same thing. So we defined its complex derivative it's a number, it's a complex number. So so that it's a linear approximation to the function, meaning that if we step from the point by some complex number h, we change the value of the function by approximately something proportional to the derivative. So also we substituted just real h and purely imaginary h. We proved that the corresponding function f to just r squared, treated as a pair of functions with real values, is in this case differentiable, real differentiable map at z node, which is so at the point x node comma y node, and we considered its matrix of partial derivatives. So here f takes the pair x, y to the pair u, v. So it's defined since the function, the map is differentiable, and by the property of these Jacobi matrices or differentials, again it provides linear approximation to the map. So f of x node y node plus h is f of x node y node plus this matrix as a 2 by 2 matrix applied to h, where h is treated as an element in R squared. Well, not equal, but is almost equal, so is close to. So since both this guy and this guy are defined uniquely, can you rotate the camera? We get that they are related by the standard embedding of complex numbers into matrices of the size 2 over real numbers, which takes A plus Bi to this matrix. So in particular, since we established this relation between complex derivative and real derivative, we get, well, look at this matrix. We get the equations on partial derivatives. So from this interpretation, they're absolutely clear, and they are called Cauchy-Riemann equations. So this was basically the end of Tuesday lecture. Let's talk more about geometric meaning of complex derivative. So for this, imagine that we have our set G on which the function is defined, a point Z node in it. So we have this function f corresponding to f, so to r squared. And imagine that we have an interval and two maps, gamma 1 and gamma 2, with values in G. So we treat an element here as a parameter t, time. So let's say that gamma 1 of t0 equals gamma 2 of t0 equals z node. So looking at the images, we can draw something like this. So this is gamma 1, and let's say this is gamma 2, starting from here and ending here. So we have their tangent vectors at this point. So the vectors of speed. So this is gamma 1 dot, and gamma 2 dot, and this is, let's say, gamma 1 dot. And there's an angle between them. Now we can compose them with f. So instead of doing it symbolically, let's see the image. So this is f of this set G. There's f of z node, and so we have two maps which are compositions like this: f composed with gamma 1 and f composed with gamma 2. So we again can symbolically present this like this, and maybe this became much longer. And again we have the corresponding vectors of speed. So let's say that this is f composed with gamma 1 dot, and maybe this is f composed with gamma 2 dot. And again, there is an angle here. So by our Tuesday lecture, the interpretation of this real derivative matrix, which certainly corresponds to complex derivative, is that it's a 2 by 2 matrix which takes the derivative of each of these paths to the derivative of their images so this vector goes to this vector goes to this vector, so it's a 2 by 2 matrix, and these are just vector columns, I think. Now, so what do we know about this matrix? This matrix is the one satisfying Cauchy-Riemann equations, so it's of the form A, B minus B, A. And we remember that if we treat this differently in trigonometric form of the complex number, then this matrix is like this. So a scalar matrix with real numbers here times the rotation matrix. Now, I won't write this down. This is elementary linear algebra, but this rotation matrix certainly preserves all distances. So we have Euclidean metric, and all distances are preserved. So, but since distances are preserved, triangles are preserved, so angles are preserved. So this matrix preserves both distances and angles. Now, this matrix certainly doesn't preserve distances. It dilates, but it preserves angles too. Right? If we take a vector and another vector and then dilate them 3 times, then the angle will be the same. So just to put it on the blackboard, preserves absolute value and angles, and this preserves angles. So composition also preserves angles. Now, looking at that picture, we see that the marked angles are the same because one of them is the image of the other. So such maps, by the way, are called conformal. So F G to R2 with such property at every point is called conformal. Good. So maybe that's enough about geometric properties of complex derivative. Are there any questions about this? So I don't think this will be used a lot in the course, but this idea of considering paths, it will appear again and again. So in a way, the difference between real analysis and complex analysis is that in complex analysis, you always, even though later there'll be usual analytic considerations with limits, with power series, and so on, we'll start them immediately now. There's also geometry present all the time, the geometry of complex plane. Good. So before starting the next topic, let's just emphasize why it's important. So remark, so far the only supply of holomorphic functions we have is polynomials. So we proved on Tuesday that constants are holomorphic, the identity function x going to x is holomorphic, then sums and products are holomorphic, so polynomials are holomorphic functions. But today we'll study in a way a universal way to produce holomorphic functions, namely we'll talk about power series. So power series is a formal expression of the form so to make it informal, let's say that, so in the formal expression all coefficients are complex numbers and z is a variable, but to make it informal we can say that z is also a complex number. So we say that, so recall, because this certainly was in the usual analysis course, series converges absolutely if the sum of absolute values converges. So we want to discuss what's called radius of convergence. So let's talk about this. So radius of convergence. So suppose we have these series. So in particular we have coefficients. So define a set. It's a subset of real numbers. It's all t greater or equal to 0, such that the set is bounded. Certainly it's defined for a given series. Clearly all cases are possible. In particular, it could be that this set simply consists of the element 0. But anyways, we can define ρ, which is supremum of t. So this means that for any number less than ρ, this expression is bounded. And consider the open disk with a center at 0 of radius ρ, and some element z, some number z inside. So what I want to say is that for this Z, the series converges absolutely. And let's see this. So we can find Z, then T, then rho, so a number in between, and certainly T is in T. So when we find this, let's consider this expression. Then we can rewrite it. So and now let's say that these ones, since it's a bounded set, are always less than some number m. So then we can estimate this by some now notice that by my choice, sorry, this is radius. So by my choice, this number is less than 1. So take m outside of the brackets, and we get by the way, so this series converges. So it has a limit. So then the whole thing is estimated from above by something which converges. So it converges as well. So this series are called geometric series. And do you know their limit? So this actually equals m times the sum of these. Do you know the sum of these? It's 1 over 1 minus good. So we've proved that so inside this disk, the at every point the series converges absolutely. So this is the disk of convergence, and rho is the radius of convergence. So let me write this as an outcome. So let me put this as a remark. For rho defined above, the sum of these series defines a function call it f of z from this disk of convergence to complex numbers. So since we're asking the question, which was the remark there, we need a supply of holomorphic functions. So the remark is that in a little while we will prove that f of z is holomorphic in its disk of convergence. Good. So this is our next goal, and the goal is achieved by the following lemma. And then a big theorem. So lemma. The series and its formal term-wise derivative have the same radius of convergence. Call it rho. Corollary. So for f of z being sum of the first one, this one defines a function from the disk of convergence to complex numbers. What we won't know even with the lemma, so we need to prove separately. That the derivative of f equals this sum. So this is a formal procedure. We just term-wise took derivative of a monomial. We will do this, but the lemma is simpler than that. So let's prove the lemma. So proof. Let's go in this direction. So so we have T, this set for first series, and T prime is this set for second series. And let's say that M bounds, so T node is in T. M bounds the set of An T to the N. So now let's see what we can T node. What we can do for the second series. So let's choose any T which is less than T node. So in particular, certainly it's also inside T. Now let's write the estimate. So this is the term of the second series. and let's start rewriting it. Then t node to the n, then t node n minus 1. And then we have extra t node, so times 1 over t node. So notice that t is arbitrary, but t node we fixed. So now this expression is bounded by m. So we can take, so this is less than m by t node. And what remains is n times t node n minus 1. Now, this sequence converges to 0, so this one is bounded as well. Because, I mean, the limit is 0. Yeah, that's it. So this one is an estimate. This one is bounded, so it has its own upper bound. So this is less than m times n by t node, bounded. So we get that that any t less than t node is in t prime. For any t node in t. So we have inclusion in one direction. So we have inclusion of sets in one direction. So let me leave the other direction as exercise. So the other implication is clear. So as an outcome, we get that supremum of t equals supremum of t prime, and call it rho. Good. So this was the easier part. Now let's talk about the difficult part. So in a way, this is the central theorem in section whatever 4. And this is the first statement with non-trivial analytic proof in the course. Let's try to do it carefully. Certainly it's covered in the book, but I'll just try to discuss it in such a way that we'll see what's going on slowly. So theorem. So suppose that this sum of series converges absolutely in the open disk like this. So then the sum is holomorphic in the disk of convergence and the derivative is exactly the series we discussed before. Okay, so we'll do the proof slowly, just to emphasize what's going on. We'll check, so method of proof. Check differentiability of f of z at a given z node. So by definition, so now there'll be some delicate choices of subsets in this disk. So so we have this disk, so geometric picture. So don't forget that disk is open, so so we're always strictly inside. So this is the disk around 0 of radius rho. Now we step in, so there's z node somewhere here. We step in here so that they would be completely inside the disk. So this is the disk of radius r. So and now we'll check differentiability at this point. So there'll be this step out h, and it will be such that we would be completely inside here. So this is h. So we chose h. I think it's better to see here. So this is r, this is z node. H is less, so this part is r minus z node, and h is less than it. Okay. Good. So we know by the previous lemma which I just derived, so the series maybe converges absolutely since we're inside the disk of convergence. So the sum is our candidate for f prime of z node. Then, well, this means that we expect limit be 0, so this is h. And we want to prove it. So for this we have the so this thing is the remainder term denoted by epsilon of h. So we'll prove that the limit of epsilon of h for h tending to 0 is 0. And so let me write carefully what it is. So this epsilon of h is sum n equals. So definitely constant terms just canceled out. So there's nothing to discuss. So n equals 1 to infinity, and then an 1 over h z naught plus h to the n minus z naught to the n minus n z naught to n minus 1. So we want to prove that this thing as a function in h has a limit equal to 0 as h tends to 0. That's what we'll do. It's a careful calculation. So we'll continue after the break. Are there any questions so far? So today we are going very much by the book. And yeah.
I actually do have a question.
Uh-huh.
At some point, you distinguished between formal and informal. I think. And I was wondering what that means.
So no. When I say formal series, it's just the set of coefficients, basically.
Okay, yeah.
So I mean, z there is a variable, but if you when I say just series, it means that I'm planning to substitute some value of z.
Okay.
So it's just that. At this point, it's not like a definition or something. Mm-hmm.